Let's discuss piecewise functions. So a piecewise function is a function that has several different equations depending on which section of its domain you are in. So I'm going to go ahead and write one up here. And so this little squiggle here is one of those curly brackets, and that indicates that we have that grouping of functions. And so this piecewise function I'm going to define to be 2x minus 1 if x is less than 1. And it's equal to 5x squared if x is greater than or equal to 1. Now, piecewise functions can be defined for any sections of the interval negative infinity to infinity. So this one has every element in its domain, negative infinity to 1, and then 1 included to infinity. So this one does span negative infinity to infinity, but that is not a mandate for piecewise functions. They can be as small or as large as the problem defines. So this is kind of strange, right? We see these two different equations, but these things really do come up quite a bit. And so we'll look at a few of those real life examples towards the end of the video. But it is not uncommon in life that we see a function will take on certain characteristics up to a certain point, and then change those characteristics a little bit later on. So let's go ahead and just play with this for a minute. And what I want to do is just evaluate the function at a couple points. So let's say I had f of 1. Typically, if we have a function, we know we just take that 1, we plug it into the x, and we get the y value back out of it. But then here the problem is we have two different equations, and which one do we plug into? Well, this is determined by that domain element. And so our x value is 1. We need to think about, is that less than 1? No, 1's not less than 1. Is 1 equal to or greater than 1? Yes, it is. So because the 1 falls into this range of, this domain, we're going to use this equation right here. So I'm going to have 5 times 1 squared, and 1 squared is 1 times 5 gives me a value of 5. Let's look at f of negative 2, just again making up some values here so we can see what's going on. So negative 2, is negative 2 less than 1? Yes, it is. So that tells me I'm going to be using the first equation. We were told that these piecewise functions are functions, which means that we can't have two different equations working at the same time. I couldn't say plug into this equation and this equation because that would give me two different answers. So we only will have one correct equation that we're going to be choosing. When we plug in that negative 2, we get negative 4 minus 1, which is a negative 5. And let's just do one more. Let's say we have f of 3. Is f of 3 less than 1? No, it's not. Is f of 3 greater than 1? Yes, it is. So 3 is greater than 1, so we're going to plug into the second equation. We'll have 5 times 3 squared. 3 squared being 9 times 5 is 45. So that gives us an idea of how these piecewise functions are working. And one very important skill that we're going to need to know is how to graph these piecewise functions. So I'm just going to sketch out an xy plane. Of course, if you had graphing paper, it'd look a little bit prettier. But I'm going to graph these two equations. 2x minus 1, and while I'm graphing these, I should say too, I'm going to assume no knowledge of transformations. If we knew how to graph transformations, this would be a much easier process. But I'm going to assume that I don't know how to graph transformations yet, so I'm going to rely on my x, y tables. So this top equation, 2x minus 1, I need to graph this when x is less than 1. So I already have 1 point. I know that this second point here, that fell into that equation. So if I want to set up a little xy table, I already know at negative 2, my y value is negative 5. But I know if I have a line, which this is a line, I need at least 2 points. And so I'm going to graph actually 1, and that seems a little bit counterintuitive because 1 is not included in the domain. This function ends just before 1. So why don't I, for just a second, then I'm actually going to put 0 in here. We'll do 0 and 1. So let's find both of those. So 2 times 0 is 0, minus 1 is negative 1. And then 2 times 1 is 2, minus 1 gives me a 1 there. So now I have 3 values to plot. And like I said, that last one we need to talk about because that one's not really even there. So we'll talk about that in just a sec. Negative 2, negative 5. Then we have 0, negative 1. and then we have the point 1, 1. So if I were to connect these 2 points, let me just go ahead and connect these two for just a second. We'd have a line, and this would be correct if it wasn't a piecewise function, if we just had that one top equation, but the problem is this thing ends when we get to 1. We want to have all values less than 1. So when we're hitting 1, wherever that value might be, we need to stop our graph. And so that's the advantage to actually plotting what that number is. And so we know that f of 1 is equal to 1. So let me come back and place that point on here too. But when I place that point on my graph, I'm not just going to put a little circle there, a little dot. I'm going to put an open circle because that's indicating that I'm stopping and not actually reaching that point. And then I'm going to connect my dots, like so. So the reason I would include that, if I didn't include this stretch of line right here, if I just stopped, say, at this point right here, I would have left out all values between 0 and 1. But this line passes through when x is equal to, say, 1/2 or 1/4. So I've got to make sure I have all those values, and the way we indicate that we have to stop is with that open circle. Let's move on to the 5x squared. So again, I'm going to have to set up an xy table. So I'm going to choose this time, well, a good starting point is 1 because I know that 1 is included. It's a valuable point to start at. So it's always a good idea to choose those end values. I'm also going to choose 2 and say 3 because we had 3 in the table from before. And in fact, we know that f of 1 from before. That was 5. We knew that f of 3 was 45. And I can plug in my 2. 2 squared is 4 times 5 is 20. And so the value is getting really large very quickly. So I'm going to do a rough sketch of this. At 1, we have a y value of 5, 2, 3, 4, 5. I'll be right there. And then from there, at 2, it goes up to 10. So 6, 7, 8, 9, 10. Gonna be way up here. And again, this is a little bit of a ballpark because I don't have graph paper on my screen. And I'm going to connect my dots, and I do know quadratics with a curve, so it's going to be increasing faster and faster like so. And that line needs to come down and touch. So there's an example of one of my piecewise functions. Let's take another one. Just name it something different this time, so we'll go with g of x. So this piecewise function has the following equations. X squared if x is less than -1. 2 if x is between -1 and 0. And then we'll do the square root of x if x is greater than 1. So we have 3 different equations this time, and we can have however many equations that are dictated right by the scenario or by the problem. So here we have 3 different equations, and we notice that this time we don't have a continuous domain from negative to infinity. We go to -1, we include the -1, we go to 0, but then we don't have anything from 0 to 1. So there's actually a space of time here where we don't have those values. The domain is not just negative to infinity. So let's go ahead and just practice finding a few values just to make sure we have the hang of it. So what if I were to ask for g of -2? Well, -2, I need to look at what interval it falls into. Obviously, -2 is less than -1, so I'm going to use that first one. -2 squared would give me 4. Next, I'll find g of -1. Well, -1, not included there. It is included there, so I'm going to use the second equation. That equation tells me the answer is just always 2. It's a constant function. Let's find g of 0 next. Well, I don't have 0 here, and I don't have 0 here. I don't have 0 anywhere here. So actually, g of 0 doesn't exist. This function is never equal, the x value is never equal to 0. So we'd say DNE or does not exist. And I'll do one more. Let's say we have g of 5. Well, I plug into that second equation, and I have the square root of 5. Which doesn't have a nice pretty value, so I'll just leave it as the square root of 5. It would be 2 point something, and so I'll just leave it as the square root of 5. So let's come back here now and let's graph this piecewise function because I think that tends to be a little bit harder. So if x is less than -1, we have that x squared function. So let's set up a little xy table for that. And because it's quadratic, I'm going to make sure I have at least a few points. And I'll say start at -3, -2, -1. And again, that -1, why am I including it even though we never actually get there in that equation? Well, I need to know where I'm getting up to. I need to know where I'm kind of supposed to stop. So we'll plug this in. -3 squared is 9. -2 squared is 4. -1 squared, we already had that. No, we had the -2 squared already. That was 4, and then -1 squared should give us 1. So I have a few points here to plot. So -3, we had the 9. -2, we had 4. 1, 2, 3, 4. -1, we have 1, and that one's going to be the open circle. The other ones weren't open circles. Why, again, is this one the open circle? Because we don't actually get there. These others we're going to pass right through, and it's going to have that curved nature to it. It should be a little smoother curve, more like that. Let me just draw that again one more time. So it should be a smooth curve, like so. That looks a little bit better, and it's curving up more and more until it gets to that open circle. Then we have the next equation, which is 2, and that's between -1 and 0. So not a lot of x values I can plug in there that are going to be whole numbers. We can always use fractions as well, but I don't really need to because I know no matter what x value I choose, my y value is always going to be 2. It's just constant. And so I'm going to use the -1 and the 0 for my x values because those give me the endpoints. At -1, we see that we have 2, which would be up here, so that line's sitting right next to where the open circle, the closed circle would be. And it goes over to 0 at 2 as well, so right here, but with an open circle, and then I have to connect those two things, my line there. And then we're going to move on to the third equation, the square root of x. So a good starting value to plug in here would probably be 1, because even though we don't get to it, we need to know what we're getting close to. The square root of 1 is 1. I'm going to skip 2 and 3 just because I don't want to have an ugly square root like that. I just want to have whole values. So I'm going to go up to 4, and the square root of 4 is 2. And then I'll maybe go to 9, again just for the nice whole value. I get a y value of 3. So we get to choose what x values we want to plug in as long as they're inside the interval. So I chose my perfect squares here. So at 1, we have 1. At 4, we have 2. 5, 6, 7, 8, 9, we have 3. And there would be our square root function. I've made a mistake though, because at that 1, it should have been an open circle, not a closed. Let me try that one more time. An open circle, not a closed, because we didn't actually get there. So I need to make sure that on my non-included points, that's the wrong one, on my non-included points, the 1 needs to be an open circle because I don't actually get there. And so that would be the graph of this one. Again, there's a little bit of a disconnect there. There's a little bit of space in there that shouldn't be touching. So graphing these things the same way that we did earlier, just we have to remember to stop at their given intervals. Now, once we learn how to apply those transformations and once we understand these shapes a little bit better, it's going to be the same exact idea. We're going to be able to graph these things without doing the XY tables, but we're going to still have to make sure we start and stop at given positions. So I told you guys these have several examples, and so I'll just kind of list off a couple, and then we'll think about one in a little bit more detail. So one great example would be taxes. Taxes, I think, are always misunderstood because people don't usually do their own taxes. You always think that you always just plug it in the H&R Block and it kind of works out for you. But one of the common misconceptions I see is this idea that, you know, if you make between, say, 0 and I'm just going to make up these numbers. I don't know exactly what they are. Say $0 and $10,000, you pay 10% tax rate. Then if you make between 10,000 and 25,000, you pay, just making up these rates, 15%. It's not a dollar, that's a percentage. And that just keeps going up and up, right? And so there's this common misperception that if you make $100,000 and let's say that the tax rate there is 25%, you pay 25% of that full $100,000. No, you pay 25% on the amount over the previous tax bracket. So what you see is kind of the tax rates, you pay a small amount, then you pay a slightly larger amount, and slightly a larger amount, but each of those fall in the individual tax bracket. So you have this kind of disjoint graph where it's going up at different rates depending on which amount you're making, different tax brackets. So that's one example of a piecewise function. Another example would be stamps. If we think about the postal service, and I honestly I don't know how much a stamp is these days, and I don't know how much weight it gets you, so I'm just going to make up some numbers here. Again, we'll kind of be in the ballpark, but let's say that one stamp is 50 cents. So I'll say 0.5, and these are going to be in dollars, my y-axis. And then, of course, that'll buy you different amounts of weight, because if you send a single sheet letter, you only have to put one stamp on there, but that one stamp, it doesn't matter if that letter is thin or if it's cardstock, you're going to be paying the same amount for that one letter. If it's 1 ounce to say, let's say 3 ounces, you're putting one stamp on it. But once it hits three ounces, well, now it gets too heavy, and now you have to pay for a little bit more. And so now we're paying for 2 stamps. We have to put a second stamp on there, and that second stamp will cover us until we get to, say, 6 ounces. And again, I'm just making up these numbers. I don't know exactly what the Postal Service is charging. But there's not the option that if my letter weighs in at 4.5 ounces, I can't cut that stamp in half and put 1.5 stamps on there. I have to pay for the whole next stamp. And then if I have another couple ounces, let's say I get up to 7 ounces, well, now I'm putting yet another stamp on there. I'm up to 1.5. And so we see that we get kind of this step-looking graph, and this is called a piecewise function. This is a piecewise function. This is also called a step function. Step functions, we can see that kind of looks like these stair steps, because we can only pay for that whole stamp. We can't cut that in half. We can't pay for just part of it. The exact same idea is something like a parking meter. If you're going to pay to park, let's say for 3 hours you have to put in 50 cents. But then once you get past 3 hours, you got to put in another 50 cents. You can't cut those quarters in half and start paying with half quarters or less smaller increments if that's not what the meter will take. And in fact, even now, a lot of parking lots have switched over to electronic billing systems. And so you put your credit card in at a little central station, you put that up on the dashboard. A lot of them still work under this old same measuring device where you can't pay for part of your time. If you're staying for 3 hours and 15 minutes, you can't pay for 15 minutes. You have to pay for the whole time increment. So even though we've switched over to electronic, and it's not the same idea as putting quarters in, a lot of them have kept that same system. And so these are a few examples of piecewise systems, not the only ones. There are other equations just in life where, we might get to a boiling point very quickly, but once an object gets to its boiling point, or once an object gets to a certain temperature, it kind of levels off for whatever reason, and then might spike down the road. So temperatures tend to follow these piecewise functions. So they are valuable to recognize, one, how do we plug into these piecewise functions, and then two, how can we get the graph to really understand what are we looking at.